All right, I think we are live. Let's try this again. Hopefully, this time the connection remains stable, or at the very least, remains stable for however long I'm going to be streaming. What's up, guys? This is Dem Keys, and I'm just going to do the intro again because, I had to restart the stream. Today, we're going to be exploring clustering. More specifically, I think we're just going to focus on k-means clustering. There's a bunch of different types of clustering that scikit-learn supports, and I want to explore all of them. But all of them, each one is going to take time. I need to, I need to look at each one of them in detail. So, like I was saying previously, before I had to restart the stream. First of all, Q10, I don't know if you're still here or not, because I did have to restart the stream, but hello, hello. Welcome to the stream, and thank you for the lurk. What was I saying? Yeah, so along with learning deep learning, I've also been very much interested in EDA, which is exploratory data analysis. The whole idea there is to try and find patterns in data and try and find relationships between the various variables that you have in the data. And I'm super interested in that kind of thing. I want to try and find whatever information I can from massive data sets. And the only way that you can do that, because if you're looking at a small data set, you could kind of see the patterns in the numbers, but the bigger the data set becomes, the more variables you have in there, and the more let's I guess the bigger the data set becomes, that's the best way to say it. The bigger the data set becomes, the harder it can become for you to just see the patterns in the data set itself. So then you have to use these kinds of techniques to find patterns in the data and try and find connections between the different variables, and I don't know what more. To be honest, I'm that's I guess that's one of the reasons I'm trying to learn EDA, so that I can figure out what kind of patterns what kind of useful information I can extract from a massive data set. And clustering is one of those things. There's a bunch of other stuff as well that I need to check out. Before I had to restart the stream, I was explaining that while learning deep learning on the side, I've also been learning EDA. I've also been learning stats related things, but more specifically EDA. I've been focusing more on data analysis because that's a field that I'm interested in. And where was I going with this? I don't remember where I was going with this. So, in scikit-learn, which is the library that we're going to be using, there are a couple of different methods in both supervised learning and unsupervised learning, and we're going to be exploring a bunch of them. Two things or three things for the time being that I really want to focus on are clustering, principal component analysis, and there was one more thing, covariance. This thing. These are three things that I want to focus on right now, but there's a bunch of other things as well. Like if I just look through this list, there's a bunch of other things that basically I want to try and apply these various techniques to data analysis, to more specifically exploratory data analysis. And I want to see what patterns they're able to reveal or what information they're able to reveal about a data set. Speaking of data sets, I spent yesterday doing stuff on Kaggle. I set up I set up an account on Kaggle. I'd set up an account like I'd set up a different account on Kaggle as well, but yeah, I set up an account on Kaggle yesterday, and I like how they've kind of gamified the data science journey. Like they do this whole thing with the achievements and rankings and stuff like that, and various activities that you do. Those are basically incentives to increase your rank. So in a way, like it becomes kind of a game. It becomes like a badge of honor, like increasing your rank by doing the various things. But like keeping that aside, I was just going through the notebooks and stuff. I was going through the tutorials and notebooks because I'd anyways started going through the Kaggle courses previously, but I was doing it without an account. In this case, now that I'm doing it with an account, so there's a sort of tracking thing going on where it tracks that, oh yeah, okay, you finished this course, you finished that course, and stuff like that. And of course, a huge bonus of doing this is that a huge bonus of not adding having an account is that I can actually run the notebooks. I don't think I would be able to do it without an account. I can also create my own notebooks and oh yeah, I spent time yesterday looking at the various data sets that are available. Dude, okay, Kaggle, let me just say Kaggle is great. And this is coming from somebody who's very much a beginner in data science, someone who's very much a beginner in data analysis. Kaggle seems great for research purposes and learning data science. I don't know how good it is for people in who are how do I say this? Who are at a more advanced level in data science. Because I'm not at that level, so I can't really say anything. But at least for beginners, there's a lot. There's like there's a lot of stuff for beginners to do. There's a lot of useful resources to help you. There's a lot of community resources. There's a shitload of data sets, dude. And adding data sets to your notebooks is super easy. It's not like you have to spend time download. I mean, to a certain extent, yeah, you have to, but it's not it's not as tedious as if you would have to download the data set onto your computer and then extract it and import it into your project and stuff like that. In on Kaggle, if there's data sets on Kaggle already and you have your notebook in or on Kaggle, you've created your notebook, you can easily add any of those data sets as input, assuming they're public data sets. I don't know if you can have private data sets on there, but there's a lot of public data sets for various purposes. At some point later on, and this is like way later because it's going to take me some time to set this up. At some point, I do want to set up my own data set that I want to share on Kaggle. I have some ideas for the way that I want to go about doing it. It's going to be a sales data set. That's what I can say for now. It's going to be a sales data set, but it's going to be a little more sophisticated than just random data. It's going to have like customer behavior, customer purchase behavior, or purchase patterns. I'm going to try and make it in such a way that like this data set, when somebody analyzes this data set, they're actually going to find patterns in there, various types of patterns. What kind of patterns, I'm going to have to see. I'm still thinking about the whole thing. Fortunately, the Faker library is a thing. It is available, so I'm definitely going to be using the Faker library. But there's going to be a lot of work for me to do there. There's going to be a lot in terms of, because I'm going to have to create the behavior. I'm going to have to define I'm gonna have to define the behavior. You know what? We can get into that later. Maybe I'll do the coding for it on stream. Uh, yeah, yeah. I'm gonna have to sit down and write down all the points, like what I want this data set, because I already know what I want the data set to look like. I already know what kind of columns and stuff I want in the data set, but there's specific customer behavior patterns that I want to introduce in there. Customer um, purchase patterns that I want to introduce in there. I want to create patterns in there, just so it resembles more closely a real world data set. And having seen a similar real world data set to what I'm trying to create, I feel like I would be able to mimic those behaviors. But again, I would have to create those behaviors. I would have to code those behaviors, and it should be interesting because what I'm going to do is I'm going to create a behavior. I, I don't know what to call it other than a behavior. Maybe we can call it a behavioral pattern. This is going to be a pattern, and every customer that the business has, every customer is going to have this. They're going to have their own behavioral pattern, their own behavioral purchase pattern. What it's going to be based on, I'm going to have to see. But I can make it super dynamic. Like, I have some crazy ideas for stuff that I want to do, and I'm glad that I came up with this idea of creating a behavioral pattern that the customers are going to follow. Like, every customer is going to have their own specific needs, right? Based on their needs, they're going to be purchasing stuff, and their needs are going to be part of their behavioral pattern. So what I'm going to need to do is create I'm going to need to create a structure that represents this behavioral pattern, and every customer is going to have their own behavioral pattern. And then based on that, we're going to generate records. We're going to generate purchases for each of these customers. So based on their behavioral pattern, it's also gonna based on their behavioral pattern, it's also gonna change what items they buy, how many of those items they buy, and a lot of stuff. There's a lot of stuff that I want to define. Dude, I have ideas, man. I have a lot of ideas. I want to work on this data set because I feel like this is going to be a fairly common data set, or this type of data set that I'm creating. It's going to be a fairly common sales data set. But this is something that I want to create and share because I feel like, having seen a similar data set, I feel like others would also be able to benefit from this kind of a data set, trying to explore this kind of a data set, trying to visualize this kind of a data set. But before any of that, I need to explore a similar data set that I have to try and see if I can find patterns in it. Because I haven't done that yet. I mean, I found patterns in the sense that I was able to visualize various things and create pie charts and create bar graphs and stuff like that. But that's about it. And I was able to kind of create stats on some of the more easily obtainable data. I'm not sure how to say that. Like, it was basic stuff. It was counting the number of orders and average sales, or most sales, or most purchased items, stuff like that. Very easy to calculate stuff. Very easy to obtain data thanks to pandas, because pandas gives you the tools to be able to pull all of this data very easily. But I'm trying to find more complex relationships between the variables in the data. Now, what am I looking for? I don't know. That's the issue. That is why I wanna learn all of these different techniques so I can apply these different techniques to that data that I have and see if I can if I can pull something useful from it. The good news is I'm not limited to just the data that I have. I have the entire like Kaggle dataset catalog at my at or available to me. I was about to say at my disposal, but I mean, yeah, yeah, that's yeah, or at least the public, I should say the public data set. Again, I don't know if private data sets are a thing there. I'm gonna have to see. I think private notebooks are definitely a thing. I don't know if private data sets are a thing. I'm gonna have to check. But the massive public catalog of data sets, they are available to me. So if I want to do EDA on any of them, I can do that very easily. I've also been exploring. How do I say this? I've been trying to understand the sort of ins and outs of Kaggle notebooks. I'm trying to understand the tech that's around it. Or I mean, I shouldn't even say the tech. I was kind of trying to get an idea of the tech, but I'm to be honest, I'm more interested in the packages because the container within which your notebook is created, at least from what I understand, I don't know to what extent that information that I read was accurate, or if it was accurate, then I don't know if it still holds up now. Like maybe I was reading old information. I'm not sure. But apparently, the notebook that you're creating, it's being run in an environment that's running within a Docker container, and because of that, you're able to have a Python environment in which you can install various packages and stuff like that. So I kind of want to get an idea of the environment within which my notebook is running. So that's why I need to do some research. Maybe somebody has made a oh shit. Okay, maybe someone has written a Medium post, or maybe somebody from the Kaggle team themselves have written like a blog post or something explaining the internal explaining the internals of Kaggle notebooks. I have to look it up. I want to get a better understanding of it. So far, it does seem like a lot of the libraries that I need, they're already installed. A lot of the packages that I need in my projects, or at least the ones that I use right now, a lot of them are already installed. Stuff like NumPy, Pandas, scikit-learn, all of these are already installed in the environment. I don't know if PyTorch and TensorFlow are already installed or not. I'm gonna have to see because yeah, I'm gonna have to check. I haven't tried it out yet. They are supported, which is a good thing. I think I mean I don't think I would be limited in what yeah I don't think I would be limited in what is and isn't supported in terms of like the packages. But okay, yeah, I do want to get a better understanding of how these notebooks are working, and more specifically how that environment that's being set up, how it's running, what it's running inside. What else? What else? How did I get to this point? Well, okay, so I'm excited to dive deeper into Kaggle stuff because there is a lot that I can explore, and I fully intend on exploring it. Even the stuff that I'm learning here, because on Kaggle, I'm okay. Let me show you where I am on Kaggle. Hold on. Let me just Okay, Kaggle learn. Okay, let's do that, and we should be good. All right, so this is the Kaggle courses thing, right? These are free courses that are available. I don't know if there's a paid course thing. I haven't checked, but like these are the free courses available. There's also stuff that's been set up by the community. Lots. There are lots of, I guess you can call them courses as well. They're notebooks that have been set up by the community to teach various things. So I mean, in a way, you can call those courses as well, because like they're notebooks that have been set up with like a bunch of text and a bunch of code cells that you can execute to to basically run code and see how it's working. But yeah, this okay. So right now, I just for the sake of completing the thing, I went through the intro to programming section, and I think I also went through the Python section. I don't remember. Let me take a look. This was just for the sake of completing it. It's silly, but I just wanted to complete it. I wanted to see what what it was going to look like if I did complete the thing. Yes, I believe. Uh, Actually, no, I don't think it was this. I think it was the intro to programming thing. I didn't need to do this at all, but I wanted to do it just for the sake of seeing what it looks like when you complete a full thing. It's kind of cute. So when you finish this, when you finish one course, and there's like a bonus lesson as well if you want to do the added stuff. Once you finish this thing, you get a certificate for completing that course. I like that. I like that. So each of these lessons in the course, it has a tutorial section and an exercise section. The tutorial section is just text for you to read, and they'll also have code cells that are showing some of the code, as examples to demonstrate stuff. And then you have the exercise, which is an editable notebook that opens up that you can step through each of the cells, and they'll give you questions and some pre-made code that you need to edit to basically they'll give you a bunch of different problems that you have to solve. Let me just put it that way. And they have their own mechanism set up for checking if whatever answer you have given is accurate or not. So yeah, I went through this entire thing. This was why I didn't stream yesterday. I was busy just doing this, and I mean it was fun to a certain point. I was basically just doing these exercises for fun. It was like I don't know, brain tickling exercises. They were just exercises that make you think. And in doing that, in trying to solve a problem, you get to learn more and more about the language. If I were learning this language newly, I would have definitely learned a lot. But I mean, to be fair, I did pick up like a few tiny pointers here and there that I either didn't know or I knew once upon a time and I kind of forgot about them. But for the most part, it was just time pass. And because of that, after I finished intro to programming, I didn't bother with Python because I was like, dude, I know most of the stuff that's going to be taught in this. It's not really a good use of my time. So I just skipped it, and I went into the intro to machine learning section, because this section has a bunch of things that I don't know. This is a fairly new thing for me. This is where the fun stuff starts with data science for me. So that's why I was excited to get into this. Me heading into this with knowledge of NumPy, pandas, and matplotlib. Let me just say it's a huge bonus for me. Me heading into this with that knowledge already acquired, it's a huge bonus because it makes things a little smoother, at least for me. However, I'm going to put this out there. The way that they've designed these tutorials, they've made it so even if you're a beginner in something, it's not going to be a lost cause. It's not going to be like completely impossible for you to understand the tutorial and the exercise and stuff like that. Give me a second. Okay. Sorry about that. Give me a couple more seconds. Okay. Now, what was I saying? Yes. So they've designed these tutorials in such a way that even if you're a beginner in the various things that are required, it's still going to be relatively smooth for you. Like you might still be confused about how things are working here and there, but they kind of still guide you through the process. They still hold your hand throughout the entire process, and they in sections where things might be slightly confusing because you don't have some prior knowledge, they let you know that, yeah, okay, there's some prior knowledge required for this. So don't worry about it. You'll be learning about it in future sections. And they do teach you in the future sections. I don't know about NumPy, but they do teach you about pandas. I'm sure at some point they probably explore NumPy as well. I haven't seen it, but to be fair, I haven't explored the entire pandas section. But they have an entire section dedicated to pandas, which is this. It's right after Intro to Machine Learning. Um, you know what? Let's open this up. Let's take a look. So, creating, reading, writing. Okay, indexing. All right, this is all okay. All right. Summary functions and maps. Maps. Hold on. Okay, yeah, so I was interested in the pandas section as well because while I do know my way around pandas, there's still some advanced stuff that I haven't done. Stuff like grouping. I've done sorting. I haven't done grouping. I mean, I've done grouping through their example, but I haven't really practiced it. I should say that. I've done grouping. I haven't really practiced it. Also, there was something else, multi indexing. I think it was called. I don't remember. I remember I was trying to explore that topic at one point in time, but I kind of just got distracted with something else. But yeah, multi indexing is definitely one of the things I want to explore. One of the reasons I was trying to explore, I think it's called multi index. I don't remember. But yeah, at some point in time, I was trying to explore multi indexing so that I could understand the output given by the pivot tables function, which is also something I was trying to explore, which is, the pivot tables feature. That's also something I was trying to explore, but I kind of pushed it to the side. So at some point in time later, I should definitely revisit both of those topics because they are necessary. Actually, to be honest, okay, they are necessary, but I'm also really interested in both of those things because I've only ever done indexing in one way in pandas. I've only ever done it in one. Well, I mean, I shouldn't say one way. I should say I've never done multi-indexing. I've only ever done indexing. So by I've only ever indexed by integer location or by label or through Boolean indexing, but I've never done multi-indexing. I've also never dealt with multi-indexed data frames or multi-index supported data frames containing multi-indexes. I don't know how to say that, but yeah, I've basically never dealt with multi-index stuff. You know what? Okay, hold on. I'm gonna pause because in like 15 seconds there's gonna be an ad break. So I'm gonna start the ad right now, and I'll see you guys in 30 seconds. All right, welcome back. Um, what was I saying? Yeah, I definitely want to explore multi-indexing, and then I want to explore pivot tables because I never got a chance to explore pivot tables properly in pandas. I've been told that they give you a lot of very useful information, but from what I've understood in pandas, there's different ways to create the pivot tables, and the different ways that you use, they'll reveal different types of information about the data set, which I find kind of interesting. So I want to see, I want to, I want to get as much as I can out of pivot tables because I feel like they can reveal some interesting information about a data set, and I kind of just want to dive deep into multi-indexing because the concept seems kind of interesting to me, mostly because I've never done multi-indexing, or at least I haven't done it knowingly. But okay, enough of this. Dude, I'm excited for Kaggle stuff. I'm super excited. There's gonna be, I'm gonna be exploring. So okay, in this, where is that? Yeah, in this section, they guide you through the process of creating your first model, your first ML model. More specifically, it's a decision tree regression model. It does linear regression using decision trees. And actually, I don't know if at that point we can still call it a linear regression, because I mean, it's called a decision tree regression. So I'm not going to call it that. I'm going to, yeah, I don't know if at that point we can still call it a linear regression because like the algorithm is kind of different. But okay, I want to explore both. So we've started with decision tree regression. I want to explore decision tree regression and then also linear regression, and I want to see how the two algorithms, they obviously work in different ways. So I want to learn how both of them work, but I also want to see how they affect the final data, how they behave with the what am I trying to say? I'm trying to see the different types of results that you get in different situations when you use one versus the other. That's what I was trying to say. But yeah, okay, they guide you through the process of creating a decision tree regression model, and then fitting the model and running the model, and then you get your prediction, and then they'll show you that, yeah, the prediction might not necessarily be accurate. So this is where you need to train the model. So you measure the error, and then you change your weights accordingly, based on the error. So in changing your weights, that's where gradients come in. I think they go into gradients here as well. I'm gonna have to check. I don't remember, but they definitely show you how to measure your error. I don't remember. Um, I don't remember. Yeah, I don't remember what exactly you are adjusting in the decision tree regression model. I'm gonna have to actually, I think it's because I haven't gotten to that part yet. I think that's why. But yeah, they guide you through the process of building the model, then testing the model, and then they'll show you that, yeah, the data is the data could be, or the results could be inaccurate, and then they'll show you how to train the model so that you can get to the point where it is making accurate predictions. And then they explain further stuff like underfitting and overfitting and much more. I was about to say many more things, but it's like a few more things, because after that it just goes into machine learning competitions, which I'm also going to be making a submission for this. So they have, okay, I think Kaggle does this thing every month. They have like an I think it's just like a constantly running competition, which is great because it's one of those things where, like, anyone who joins Kaggle newly, they're gonna have a chance to make a submission. It's where was it? So it was, oh, should I just look up? Okay, there was EDA loan in the name, I think. What are you doing, dude? Fuck's sake, type properly. Holy shit. Okay, you know what the issue is? It's changing as I'm typing. And I feel like because of that, it's not registering my key presses properly. Okay. Where was it? Am I able to see it? Because this is one of those like recurring competitions where they have like a season and an episode, and it seems like every, oh, I think this is it. Loan approval. Yeah, it says season 4, episode something, and the thing started like a couple of days ago, 2, 3 days ago, I think. Yeah, here it is. So it started 3 days ago, and we have a month to go. And it says here, so yeah, this is the Kaggle Playground series. We plan to continue in the spirit of previous playgrounds, providing interesting and approachable data sets for our community to practice their machine learning skills, and anticipate a competition each month. Your goal for this competition is to predict whether an applicant is approved for a loan. Okay, that's great. That's great. Okay, so with the very basic knowledge that I have, I'm gonna apply that and try to learn. Okay, using synthetic data for playground competitions allows us to strike a balance between having real world data with named features and ensuring test labels are not publicly available. This allows us to host competitions with more interesting data sets than in the past. While there are still challenges with synthetic data generation, the state of the art is much better now than when we started the Tabular Playground series 2 years ago. And the goal is to produce datasets that have far fewer artifacts. Please feel free to give us feedback on the datasets, so and so, so and so. Okay. Uh, okay. Am I able to open any of them? Let's take a look at train CSV. Oh shit, it's an MB. This must be big. Right, so I can't view this right now. I would be able to view it if I had my other, like if I had the thing open in my other browser, but this is a private browser, so there's nothing signed in here. But yeah, I'm gonna be trying out this thing. I'm gonna be participating in this thing. It should be fun. It should be a good learning experience for me. I'm probably gonna do a horrible job, but like the whole idea is to just do something, right? This is gonna give me an excuse. This is basically a data science game jam or a data jam. Data jam. I like that. Data jam. Dude, I like the sound of that. A data science game jam, basically. Um, okay, enough with this. Let's get into clustering. We are 40 minutes into the stream, and now we're going to get into clustering. Okay, so clustering of unlabeled data can be performed with the module scikit-learn.cluster. Each clustering algorithm comes in two variants, a class that implements the fit method to learn the clusters on trained data, and a function that, given trained data, returns an array of integer labels corresponding to the different clusters. For the class, the labels over the training data can be found in the labels attribute. So this will be interesting because initially, I also want to try this out just simple arrays of data, simple lists of data. So there won't be any labels. So I'm not sure how I'm going to go about that. I think in their example, they're using the iris dataset, and that's available with scikit-learn. I think I already have that loaded as well. Earlier, before the stream, I was doing that. So they have a couple of like what they call toy data sets that are available with scikit-learn. And you don't even need to download them. You just need to load them. And then they have a couple of other data sets as well, which you do need to download, but they're still like accessible through the scikit-learn library. You would just need to start a download process if the thing isn't already downloaded and cached somewhere. Though I'm gonna have to see if caching is a thing. Caching should be a thing. I mean, it makes sense, right? For it to allow you to specify a path if it already exists. That should be a thing. But yeah, okay, we'll look into that. We'll look into that later. Um, One important thing to note is that the algorithms implemented in this module can take different kinds of matrix as input. All the methods except standard data matrices of shape and samples and features. Okay. These can be obtained from the classes in the sklearn.feature extraction module. All right. For affinity propagation, spectral spectral clustering, and db scan, one can also input similarity matrices of shape and samples and samples. These can be obtained from the functions in the sklearn.metrics.pairwise module. Similarity matrices. Okay, so this is something I need to look into. How to create a similarity matrix and what the similarity matrix reveals exactly, like similarity between what. So that should be interesting. Yeah, that should be interesting. Also, I think dbScan is part of this, so I'm going to find that. And then there's spectral clustering and affinity propagation. Okay, cool. Let's open this thing up. Is the music? Oh, the music is paused. Okay. Uh, user guide. See feature extraction. Yeah, this was I think in supervised learning, wasn't it? Or was it somewhere else? No, it was somewhere else. It was in dataset transformation. So there's some stuff here as well that I can look into. I came across this section a couple of days ago as well. But it was, I mean, there's some stuff for me to like too much. Um, are we good? I don't know if we are good. The stream kind of, hold on, the stream is buffering in my stream manager. Let me just do a thing and see if it's loading or what's the deal. Hold on. Nope, it's stable. Let me refresh the thing. The music is still going and OBS is not saying that I've dropped any frames. It's just that my stream is not loading on my other machine. So I don't know if I'm still streaming. Give me a second. Okay, okay. Things are loading a little faster now. And I think we might be good. Yeah, we're good. We're good. Jack, welcome to the stream. Hello, and thank you for letting me know. Yes, the thing loaded up properly. Oh, you're in ads? Okay. Well, let me know when you're back. Actually, you can't hear this. Okay. What was I saying? Back from ads. Jack, welcome to the stream. Hello. How are you doing? It's been a while. Also, thank you for letting me know that the thing is still live. I was concerned for a second there. I was like, is this thing about to crash? But I think it was just a small hiccup on my end. Welcome to the stream. Hello. I hope you're doing well. We are learning some data science things. Uh, how you been? I've been good. I've been busy. I've been busy learning a bunch of things. I've been busy with deep learning, learning about like neural networks and machine learning and a whole lot of data science stuff. I've been super busy with data science stuff. Been busy with streams and content stuff? Hell yeah. That's awesome. Hell yeah. So we are learning about clustering using scikit-learn today. One of the things that I wanted to focus on was k-means clustering. Try to lurk if I see you on. I appreciate that. I definitely appreciate the lurk. Thank you for that. But yeah, you're more than welcome to lurk anytime. Uh, K means. Okay, no, hold on. So there's a bunch of methods mentioned here, and I want to explore as many of them as I can. I don't think I'm gonna go into all of them, to be honest. But like I kind of do want to explore all of them. I'm definitely not covering all of them in this stream. Um, for this stream, I kind of only want to focus on k-means, more specifically just k-means, and then the others like affinity propagation, mean shift, spectral clustering, hierarchical clustering, and stuff like that. I'll do that as time goes by. I also kind of want to, how do I say this? I want to carry on learning Seaborn because I kind of just pushed Seaborn to the side, and um, Seaborn is pretty useful. Like, dude, if you take a look at the various, okay, hold on, let me bring it up just to give you an idea of like why I'm saying that Seaborn has a bunch of very useful things. Seaborn, let's say heat map. Give me a second. Okay, so Seaborn has, for those of you who don't know, Seaborn is a library. Wait, did I transition back? I think I did. Yeah, I did. Okay, for those of you who don't know, Seaborn is a library that provides you with very high level functions for doing a lot of different things using matplotlib. It's kind of built on top of matplotlib, but the high level functions in Seaborn allow you to focus more on the data visualization aspect versus having to worry about how exactly you're going to prepare the data visualization, because if you try to do very complex data visualizations with matplotlib, there's often a lot of complex logic involved there, or at the very least there's figuring out of the logic involved there, and that can take a certain amount of time. And you can save that time if you use something like Seaborn, because Seaborn provides you with high level functions, stuff like the heat map function, the cluster map function. There's also there's a bunch over here. If you look on the left side, I don't know how visible it is because the text is kind of small. But yeah, there's a bunch over here. Stuff like um, what was it called? Was it displot or KDE plot? Like these were part of something. There's scatter plot. They have, so okay. The whole idea with Seaborn is that it provides you with high level functions for doing complex things, so you don't need to worry about the underlying code. You can focus more on the data visualization aspect itself. And there's a lot of customization that you can do even with Seaborn. And once you go into the more advanced stuff, you are able to customize things a lot. I think they also have a thing. I haven't explored that yet, so like don't take my word for it. But I remember seeing something where it is not using matplotlib. It was doing something else. I don't remember what it was, but like there was a thing where it was kind of, I haven't explored it myself, but like, you know how Matplotlib has its thing where you have to set up a figure, and the figure, each figure can have multiple axes, and each of the axes is something that you draw your charts and graphs and stuff on. um, that's like your basic working, right? But Seaborn, at some point they introduced something else as well, which I believe doesn't use Matplotlib. Again, I don't remember the details surrounding it, so don't take my word for it, but there was something that Seaborn had set up. Uh, would that be? I think. Okay, let's take a look at the tutorial section. It might be mentioned somewhere here. Controlling figure aesthetics. No, no, it was in something else. Data structures accepted. The Seaborn objects interface. I think it was here. I think it might have been here. I don't remember. Uh, okay. The Seaborn.objects namespace was introduced in version so and so. As a completely new interface for making Seaborn plots. It offers a more consistent and flexible API comprising a collection of composable classes for transforming and plotting data. In contrast to the existing Seaborn functions, the new interface aims to support end-to-end plot specification and customization without dropping down to Matplotlib, although it will remain possible to do so if necessary. So this is what I was talking about. They have like their own, they have like a different way of setting things up, but you can also do it in the old way if you want. Now I don't remember if, or actually I don't know if this is still doing stuff on top of Matplotlib, or if it is just providing an interface like it. Let me rephrase that. I don't know if it is not doing stuff on top of Matplotlib anymore if you're using this, or if it is still doing stuff on top of Matplotlib, but it's providing a whole new interface for you to be able to customize, uh, your entire your plots and stuff, and then it's gonna communicate with Matplotlib in whatever way necessary to sort of convey those customizations. I don't know if I explained that very well, but like, yeah, I'm wondering if it's one or the other. Like, is this new interface still using Matplotlib for the rendering or not? I'm gonna have to explore this more at some point. For the time being, I do want to very much familiarize myself with Seaborn because there's a lot of, for example, if you take a look at cluster map, cluster map actually shows you. Did I open cluster map? So in cluster map, they also have methods here, and there's a couple of different things in terms of like customizations. There's a couple of different types of uh like if you're trying to plot something that requires certain types of computations beforehand, before the data can be plotted, you can then choose what type of computation needs to be done or what method is going to be used for it. A lot of this stuff, it doesn't necessarily happen when you're doing things on the lower level, which in this case is the Matplotlib level. And that's kind of why I'm really interested in Seaborn, because there's a whole lot of high level functions that allow you to do a lot of stuff without having to go down to the Matplotlib level and having to deal with all the customizations and stuff. Or rather, I should say, these functions allow you to do a whole lot of customizations without having to go down to the Matplotlib level and manually do the customizations. So with these functions, you would just have to specify the data and specify the type of behavior that you want. You wouldn't have to manually go and do the customization because the function handles it for you. Okay, enough Seaborn. We are going to go back to clustering. Okay. Non-flat geometry clustering is useful when the clusters have a specific shape, i.e., a non-flat manifold, and the standard Euclidean distance is not the right metric. Okay. This case arises in the top two rows in the figure above. This figure? Oh, this figure in the top two rows. Okay. A comparison of clustering algorithms in scikit-learn. Okay, so let's open this image here, and then I need to open up the. Oh, I don't think it opened the image. Did it? Oh, yeah, no, it opened it up in the examples section. Okay, so this is comparing k-means and all of the others in terms of what exactly? Yeah, I think I'm going to need to explore. I think this is the iris dataset. I'm not sure. Um, does it mention which dataset it is? This example shows characteristics of different clustering algorithms on datasets that are quote unquote interesting, but still in 2D. With the exception of the last dataset, the parameters of each of these dataset algorithm pairs um, has been tuned to produce good clustering results. Some algorithms are more sensitive to parameter values than others. Okay. Oh, dude, something that I should keep in mind. Also, I'm glad that I'm also learning deep learning side by side because there's various methods that I didn't really know about until I got into deep learning. For example, one of the nonlinear activation functions, I think it's a nonlinear activation function, I'm not sure. But yeah, anyways, it's called softmax. And the whole idea with that function is you give it a set of values and it is going to normalize all of those values, meaning it's going to take it down to the 0 to 1 range, right? But not just that, it's going to scale all of the values down so that when you add up all of those values, they always add up to 1. I think I have PyTorch installed here. Yeah, okay, I have PyTorch installed, so I can give you an example. Let's say import torch.nn. I think I also need. I think I also need torch. Okay, so let's create a tensor. Torch.tensor. Let's give it, I don't know, big values. 15 and let's say 54. And actually, I don't remember if giving big values is good or bad. I don't know. I think either way it's gonna scale it down. So we are fine. Let's say I don't know, 52. No, let's say 17, and let's have single digits as well. Yeah. Okay. Cool. All right. So now, how was I supposed to pass the thing into softmax? So let's say sf01 equals nn.softmax. No, not software. Softmax. Um, give IntelliSense a second. I don't remember what the signature is supposed to be. I know you need to pass in a tensor, but I don't remember if I think you have to. I think you need to specify the dimension as well. Maybe I'm not sure, or maybe you just need to pass it a flattened tensor. Which I mean, I've already done that. Give give IntelliSense a second. It's doing its whole analyzing the cells and stuff like that. In the meantime, we can. Oh, there it is. All right. So this is softmax, and then we call. Wait, do I need to call the class as a method? I think I need to call the class as a method. Initialize internal so and so. Okay. All right. This should return. Yes, yes. This should return. So I mean, I what I could have done is I could have just stored the result in this way. Give it a second to run. Okay. Um, all right, there is an error. Oh, it needs a float. Okay, that's fine. Okay. Give it give it a couple of seconds. All right, there you go. There's the result. But these numbers are very small. So here's what I'm gonna do. I'm gonna change the numbers to be much smaller, and hopefully that should scale the thing down even more. Nope, these are still pretty small. Let's reduce the number. I wanna show you guys the values. That's basically it. There you go. So these are the values. So this function, the softmax function, it normalizes these values. It scales them down, but it scales them down in such a way that not only are the values between 0 and 1, they're also scaled down to the extent that if you sum up all of the values in the set, they will they will equal to 1, basically. The sum of all of those values will be equal to 1. So if I do, can I directly do a sum? I think there is a sum function. Is it running? Yeah, it's trying to run. I don't remember if there's a sum function on tensor. I believe this is a tensor. Yeah, this is a tensor. I think softmax returns a tensor. Wow, this is taking a bit to run. Holy shit. Why is it taking so long? Okay, we can go back to this while we are waiting. Is it done running? Give me a second. Let me. Yeah, there it is. You know what? Maybe I should have. Yeah, maybe I should have done this. So let's print this and then print this. So if you look here, you'll see this tensor has these values, and then these values get summed up into 1. So that's something interesting about softmax, and it has a different effect when it's used in the neural network. It gets used for different purposes, but it was just kind of interesting to learn that this kind of a method exists, because I knew about normalizing values down to, the 0 to 1 range, but I'd mostly learned about normalizing individual values by themselves, not normalizing a set of values in such a way that all of the values in that set always sum up to 1. So that was kind of interesting to learn, and this is also why I'm super interested in exploring the various functions that get used in a neural network for different purposes, because each of these functions transforms the data in a different way. Each of these functions does something different to the data, and I find it I or rather I'm interested in learning how applying these methods to different types of data that have nothing to do with neural networks, how that would how what am I trying to say? I'm interested in seeing what effect they would have on data that has nothing to do with neural networks. That's what I'm trying to say. Okay. Um Getting back to clustering. Wait, there was something more here. Gaussian mixture models useful for clustering are described in another chapter of the documentation. Yeah, they were Gaussian mixture models are their own, like it had its own section. It's here. This was also something that I wanted to look into. sklearn.mixture is a package which enables one to learn Gaussian mixture models, diagonal, spherical, tied, and full covariance matrices supported. Okay, it allows you to learn the models, sample them, and estimate them from data. Facilities to help determine the appropriate number of components are also provided. All right, okay, we will explore this as well. Okay, what's next? Transductive. Wait, no, we're not done. Another chapter of the documentation dedicated to mixture models. Okay, k-means can be seen as a special case of Gaussian mixture model with equal covariance per component. I feel like I should refresh my knowledge on covariance, because wasn't covariance how much one value relies on another? Or was it how much one value relies on the change of okay, I'm not gonna try and guess it. Let me just Google it again, because I'd looked into covariance a while back. I think I even calculated covariance to a certain extent, and then I just forgot. I'd done it on like simple sets of data. Okay, so let's see covariance. Oh, I think I might have been looking at variance, not covariance. I think I might have been looking at either variance or variation. Variance is a measure of dispersion, meaning it's a measure of how far a set of numbers is spread. Oh, this is what I'd looked at. I'd looked into variance, not covariance. Okay, so I guess that is something for me to learn, and I need to relearn variance as well, or revisit variance, I should say. because there are some basic stats methods that I don't necessarily always use, but it's always good to remember that they exist. Stuff like standard deviation. I mean, okay, to be fair, it's not entirely true that I don't really use them. There have been situations where I have used them, and as I go deeper into learning exploratory data analysis, I'm pretty sure I'm going to be using them a lot more. So I should say that in the past, I haven't had to use them too much. But now that I'm having to use them, it would benefit me to remember that, yeah, these things exist. I don't necessarily need to remember any of the algorithms, but just remembering that they exist, remembering that those tools are available can be helpful. So stuff like central tendency and standard deviation and variance, and there were a couple more. I'd written them down in a list because I wasn't gonna remember all of them. The very basics that I remembered were mean, which is average, median, which is, let's say, the center value in a data set. Then you have standard deviation, which is kind of an interesting concept. I believe standard deviation was how much each of the values in the data set vary from the mean, if I'm remembering that right, because that was my way of understanding it. That was my way of visualizing it. Let me just Google it real quick. Standard deviation is a measure of the amount of variation of the values of a variable about its mean. Yeah, okay, that's right. So it's basically how much the values in a set vary from the mean of that set, from the average of that set. But yeah, these are the three basic ones that I remembered, and then a bunch of the others I kind of explored them and then forgot about them because I didn't use them. But like again, these all of these can be pretty useful in different situations. So I feel like I should be remembering them. Also, covariance. Covariance is definitely something I need to look into. Let's bring it up here. I don't know if what do you call it? I don't know if scikit-learn has an entire section on covariance. There's a thing on covariance estimation. I don't know if that's the same thing, but let's see. Covariance. Okay. So there's covariance estimation, and let's also open up covariance on Wikipedia. And what else was I going to open up? Variance. Yes. All right. Um, okay. So, in probability theory and statistics, variance is the expected value of the squared deviation from the mean, Wait, how different is squared deviation from standard deviation other than the fact that it's squared? Or is squared deviation just a whole other thing? Squared deviations from the mean result from squaring deviations. Okay. In probability theory and statistics. Wait, squaring deviations. Wait, so standard deviation should give you for each value, you should have for each value a standard deviation, right? So each value in the set should give you a standard deviation. So if I think I have NumPy already. Oh, I guess not. Let's go back up and okay, a little too up. Okay, cool. So let's go back down now. Yeah, I think we're good. Okay, so numpy.array. Here we can create, I don't know, let's just let's do that. And I don't know, let's say nd01. So that's our array. And then we should be able to calculate. There was a thing where we could, I think it was linear regression. So there was a lingress function which would give you a bunch of information. Though there was also an std function which gives you the standard deviation alone. I guess I can just get the standard deviation. All right. Give IntelliSense a minute, I guess. Wait, does NP have an array method or is it an ND array method? I forgot. My God, dude. IntelliSense goes to shit when I'm trying to stream. Though, I mean, once it kicks in for like a specific library or something, I think things become a little smoother after that, but prior to that, it's a little shit. Okay, so it works. Okay, standard deviation is one value. Why is that? Standard deviation. So are we getting like an average? Is that what's happening? Are we getting an average of, so are we calculating how far away these, okay, hold up. We can find a way to confirm this. So that's the standard deviation. Okay. Let's calculate the mean as well. Let's print out all of these values. So let's print out the mean. That's the mean. Okay. So let's do what is, so how would this go? This would this be 4 minus 3 or 3 minus 4? Let's say 4 minus 3. Okay, so 1, and then 2 minus 3 would be negative 1. Would it be negative 1? Yes, yes, negative 1. And then 5 minus 3 would be 2. And then 1 minus 3 would be negative 2. Okay. Um, all right, cool. And then we divide this by 4. We got 0. Oh, it's because this entire thing is 0. That's crazy. Okay, hold up. So here um what I was trying to test is if what's, because I don't know what the standard deviation formula is, but I was trying to test um if what was really happening was we were just getting a mean of all of the subtracted values, or the mean of the differences, basically. And that was being called the standard deviation. I guess not. So we're going to go take a look at the standard deviation. Is this deviation or standard deviation? Serves as a measure to quantify the disparity between an observed value of a variable and no, wait, okay, this is different. This is not the standard deviation. This is standard deviation. In a given sample, there are as many deviations as sample points. Summary statistics, I should look into that because that'll give me an idea of how I can get various types of data about a data set or various types of stats on a data set. Okay, summary statistics can be derived from a set of deviations such as standard deviation and the mean absolute deviation, measures of dispersion, and the mean sign deviation, a measure of bias. Okay, all right. The standard deviation is a measure of the amount of variation of the values of a variable about its mean. Okay, a low standard deviation indicates that the values tend to be close to the mean. Also, okay, but how is this being calculated? For some reason, I'm super interested in how this is being calculated. Okay, so this is our mean. Population standard deviation of grades of so and so. Wait, did it mention somewhere here what the calculation is? When only a sample of data from a population is available, the term standard deviation of the sample or sample standard deviation can refer to either the above mentioned quantity as applied to those data or to a modified quantity that is an unbiased estimate of the population standard deviation. Okay, all right. Basic examples. Right. Um, so these 8 data points have a mean of so and so. So that's our average. First, calculate the deviation of each data point from the mean and square the result of each. Oh, we have to square it? Okay, let's try doing that here. So the square of 1 is 1. How do you get a square of a negative value? You can't get a square of a negative value. You would need to take the absolute of it, wouldn't you? Or is it just 0? Here, the square is showing up as basically they take the absolute of it and then square it. Okay, all right, fine. So let's rewrite this here. So if we are taking the square, wait, what do we do after that? Right, okay. We are still dividing it by, so we are then still taking the average. Okay, so the square here would be 1, and here also it would be 1, and here it would be 4, and here also it would be 4. Okay, all right. That's interesting. The variance is the mean of these values. Oh, okay, cool. That's how you calculate variance. And the population standard deviation is equal to the square root of the variance. The square root of the variance. Right. Let's try to get a square root. Um, okay. This is expecting a scalar, right? Oh, there it is. Okay. All right. Cool. So I was only right about a small portion of it. There was still a ton of calculation to do because we calculate the mean. From the mean, we calculate the variance, and from the variance, we then calculate the standard deviation. So the interesting thing is, okay, this is technically, well, okay, no, I can't say it's technically just the mean. It's not. However, it is one value representing the variance. In a way, I guess this is an average, isn't it? Because we are taking the mean of the variance. Wait, no, the variance is, oh shit, I missed the ad timer. Okay, so there's an ad playing right now, and I guess I'll see you guys in 30 seconds. I'll take a hydration break in the meantime. I've been talking a lot. Okay, so back to what I was talking about. So, okay, variance would then be considered just one value, right? Um, does NumPy have a variance function? Is that a thing? Let me check. Or do I have to pass it into like a linear regression model? And what does this give you though? Is this variance or something? I don't think this is variance. I think this might be something else. What was it? np.lingress, I think. How do you hold on? How do I calculate variance in, okay, where NumPy variance. Oh, var is variance. Okay. All right. Shit. Okay, so 2.5 is our variance, which is basically what I was calculating here. Um, though, no, hold up. Um, variance involves squaring and then taking the mean of it. Yeah, okay. Variance involves squaring it first. That being said, variance is also a single value that is meant to represent, it's supposed to give you an idea of how much, it's supposed to give you a rough idea of how much these values vary from the mean, right? I guess it's from the mean. No, that's the standard deviation. Is it how much these values vary from each other? Like what's the comparison here? What's the what's the thing that they're comparing against? Variance is the expected value of the square. Wait, is the expected value of the squared deviation from the mean of a random variable. The standard deviation is obtained as the square root of the variance. Variance is a measure of dispersion, meaning it's a measure of how far a set of numbers is spread out from their average value. From their average, how far it is spread out from their average value. It is a second central moment of a distribution, and the covariance of a random variable. But my God, my mouse just keeps hovering over things. Okay, give me a second. Okay, yeah. Um, it's the it's the second central moment of of a distribution, and the covariance of the random variable with itself, and it is often represented as whatever. Okay. An advantage of variance as a measure of dispersion is that it is more amenable to algebraic manipulation than other measures of dispersion such as expected absolute deviation. For example, the variance of a sum of uncorrelated random variables in is equal to the sum of their variances. A disadvantage of the variance for practical applications is that unlike the standard deviation, its units differ from the random variable, which is why the standard deviation is more commonly reported as a measure of dispersion once the calculation is finished. Another disadvantage is that the variance is not finite for many distributions. There are two distinct concepts that are both called variance. One as discussed above is part of a theoretical probability distribution and is defined by an equation. The other variance is a characteristic of of a set of observations. When variance is calculated from observations, those observations are typically measured from a real world system. If all possible observations of the system are present, then the calculated variance is called the population variance. Normally, however, only a subset is available, and the variance calculated from this is called the sample variance. The variance calculated from a sample is considered an estimate. Oh, that's interesting. Okay. Is considered an estimate of the full population variance. There are multiple ways to calculate an estimate of the population variance, as discussed in the section below. Okay. All right. Going back to the definition of variance, variance is a measure of dispersion, meaning it is a measure of how far a set of numbers is spread out from their average value. So it is still technically being compared to, isn't it? Isn't it still technically being compared to um, the mean? Because it seems like, okay, when you have the variance, it's called a variance, right? But then you take the square root of that and suddenly it's a standard deviation. Like isn't that exactly what's going on? Yeah, there it is. Uh the variance is the mean of these values. So the variance is the average of the squares of the differences. The average of the squares of the differences from the mean. Okay, so that gives you an idea of it gives you an idea that on average your values are this much spread out from the mean. And then standard deviation does pretty much just that, but like you take a square root of the variance. Okay, this formula is valid only if the eight values from which we began form the complete population. If the values instead were a random sample drawn from, oh, okay. So this is if we are looking at the entire data set, not a subset of the data set. If the values instead were a random sample drawn from some large parent population, for example, there were eight students randomly and independently chosen from a class of 2 million, then one divides 7, no, then 1 divides by 7, which is n minus 1 instead of 8 in the denominator of the last formula. And the result is so and so. In that case, the result of the original formula would be called the sample standard deviation and denoted. Oh, that's interesting. Wait, no, that's interesting. Hold on. So if you're taking a subset of a bigger data set and you're trying to use that to get an idea of, on average, how far away most of the data points are from well, the average, then in the variance step, you don't divide it by the total number of samples, or not the total, but you don't divide it by the number of samples you are using. You divide it by the number of samples minus one. Dividing by n minus 1 rather than n gives an unbiased estimate of the variance of a larger parent population. That's interesting. This is known as Bessel's correction. Roughly, the reason for it is that the formula for the sample variance relies on computing differences of observations from the sample mean. And the sample mean itself was constructed to be as close as possible to the observations. So just dividing by n would underestimate the variability. Okay, all right. You know what? This was a whole thing to go into, but I'm kind of glad that I went into it because it kind of refreshed my knowledge on variance and standard deviation. And now we need to look at covariance, which seems like a much more complex topic. Okay, covariance in probability theory and statistics is a measure of the joint variability of two random variables. The sign of covariance, therefore, shows the tendency in the linear relationship between the variables. If greater values of one variable mean, no, not mean, if greater values of one variable mainly correspond with greater values of the other variable, and the same holds for lesser values, that is, if so and so, so and so, so and so, okay, the covariance is positive. In the opposite case, where greater values of one variable mainly correspond to lesser oh, so this gives you an idea of how one variable behaves as the other variable changes. So how one variable changes as the other variable changes, and in what direction it changes. Where was I? In the opposite case, where greater values of one variable mainly correspond to lesser values of the other, that is, the variables tend to show opposite behavior, the covariance is negative. The magnitude of the covariance is the geometric mean of the variances that are in common from the two random variables. The correlation coefficient normalizes the covariance by dividing the geometric mean of the total variances by two random variables. No, of the total variances for the two random variables. I think I need to look into what geometric mean is. Also, I just noticed the music has paused. I think, yeah, it's paused. Okay, great. So what does geometric mean? In mathematics, the geometric mean is a mean or average which indicates the central tendency of a finite set of positive real numbers by using the product of their values, as opposed to the arithmetic. Oh, as opposed to the arithmetic mean, which uses their sum. Okay. The geometric mean is defined by the end. Okay, so what does geometric mean reveal? Also, let's take a look at central tendency. Isn't central tendency basically how close each of the values are uh, to the central value, to the median? Yeah, let's read this. Hold on. In statistics, a central tendency is a central or typical value for a probability distribution. Colloquially, measures of central tendency are called averages. The term central tendency dates. Okay, all right. The most common measures of central. Oh, okay. These are called central tendencies. Oh, there's another thing that I looked into, but I just forgot. It's called mode. Mode is the value that appears most often in a set of data values. So basically, it's the value that you see the most. So if I have like, where's the thing? So if I have, let's say, I don't know, let's add some repetitions in here. Let's also make them out of place. Uh, all right, I think that's good. I don't remember if mode is a function. Yeah, it doesn't have. Yeah, hold on. NumPy mode. Most efficient way to find mode in NumPy. The most common n-dimensional function I see is scipy stats.mode. Uh, okay, so this is talking about using scipy, which I have scipy, but like really, NumPy doesn't have it. From scipy.stats import mode. I need IntelliSense to tell me what the definition of this thing is. Okay, I guess it's not going to tell me. Let me just pass something in and see what it says. Oh, there it is. Okay. So mode result 4. So it's the number 4 and the count is 3. Now if I introduced, I don't know, extra 5s, or let's increase the number of 2s. Now it counts. Now it says mode 2, which means 2 is the most appearing one. Dude, okay, what is the opposite of mode then? If mode counts the most number, what is the opposite? Mode opposite. Anti-mode. Okay. All right. Hold up. Import scipy.stats. Great. So here we need stats.mode. Awesome. Oh, as stats. Great. So let's see what functions are available. Or I could just look up scipy anti-mode. Return an array of the modal value in the past array. If there is more than one such value, only one is returned. The bin count for the modal bins is also returned. Okay. Oh yeah, I forgot. So, well, I didn't forget. I mean, you still need to do a little bit of calculation there because, like, in NumPy and in Pandas, for that matter, they have a unique function that allows you to get a set of the unique values in a data set or in like one list. You can get a set of the unique values so that repetitions are not mentioned in that list. So once you have your unique list for each item in that list, you can get the count from your original data set. You can count how many of those values exist, and that then I guess you can get the max out of those, and that's your mode. But what's the minimum? Like, because that same thing can be changed a little bit to get the minimum. Um, Alternative to SciPy mode function in NumPy. Yeah, I'm curious as well. Um, am I missing something here? Okay, I'm just curious. This is something silly to focus on, but I'm just curious because am I missing something here? Oh, you know what? Let me try asking Gemini. Okay. SciPy has a mode function. What about anti-mode? SciPy does not have a built-in function specifically for calculating anti-mode. The anti-mode is also known as the least frequently occurring value in a data set, is not as commonly used as the mode. However, you can calculate the anti-mode using a combination of existing SciPy functions. Calculate the frequency of each unique value. Oh, yeah, okay, so they're basically saying to do it manually. Okay. All right. Cool. So my curiosity has been satisfied. Now we can go back to this. Okay, so apparently the central tendency, which I forgot, I because I remember back when I was learning about mean, median, and mode, I'd learned that this is exactly what is called central tendency, or these are a few ways to measure central tendency. I remember this because I remember even back then I was having a confusion about exactly what central tendency is, but apparently there's a bunch of different ways to measure central tendencies, and well, this is these are some of them. Okay, measures of central tendencies are often called averages. The term central tendency dates back to so and so. Is a central or typical value for a probability distribution, which could, yep, it could either be an it could either be an average or um, the central value, which is the median, or this is interesting though. Getting a count of the most used value, though this technically wouldn't be wrong because I feel like the most used value would, in a way, affect affect the median. In a way, it would affect the average, right? If a value is appearing a bunch of times, so this is a each of these is a different way to measure central tendency. All right, okay, enough. Going back to this. Oh, that's why it says the geometric mean is a mean or average, which indicates a central tendency of a finite set of positive real numbers. Okay, and geometric mean uses the product of the values instead of the sum, and then the rest is the same, right? Yeah, you still divide it, don't you? The geometric mean is defined as the nth root of the product of n numbers, i.e., for a set of numbers uh, an, the geometric mean is defined as so and so. The geometric mean of two numbers, say 2 and 8, is just the square root of their product. Oh, it's a square root because, okay, all right. Okay, yep, square root. And then we have cube root, and then we have, I need to look, so nth root, basically. I need to look into nth root. The geometric mean is used on a ratio scale, such as growth rates of human population or interest rates of a financial investment over time. It also applies to benchmarking, which is a particularly useful, no, which where it is particularly useful for computing means of speed up ratios. What are speed up ratios? In computer architecture, speed up is a number that measures the relative performance of two systems processing the same problem. Oh, I think, okay, this is leading somewhere else, I think. I'm not sure. No, I can look into this later. It's fine. All right. How did I get here? We were at covariance. All right. So the correlation. Wait, no. Where did that come? The magnitude of the covariance is the geometric mean of the variances that are in common for the two random variables. The magnitude of the covariance is the geometric mean of the variances that are in common is the geometric mean of the variances that are in common for okay, how were we meant to calculate the wasn't the geometric mean just like you multiply it and then you still divide, right? Or is it that you're taking a square root? It's defined as the nth root of the product. Oh, so it's not dividing then. It's not dividing. How do I get the nth root? Okay, hold on. Square root tells you what number multiplied by itself will give you this number. So the square root of, let's say, 25 is 5 because 5 multiplied by 5 is 25, isn't it? Yeah, yeah. 5 multiplied by 5 is 25. Um, what would be a good example of cube root? So let's go with 2. 2 into 2, 4. 4 into 2, 8. So the cube root of 8 would be 2. Wasn't it log that gives you this answer? How do you calculate nth root? NumPy nth root. There was a thing. I'm trying to remember that. Okay, hold on. Hold on. So I forgot what I was trying to ask Gemini. I was gonna ask if hold on. Um okay. I'm trying to find out. Oh, that was log. That was log. Log tells you um x to the power of what gives you no. What was it? Yeah, yeah. Log log tells you x to the power of what gives you y. Let me just confirm that. So let's say 5 to the power of 2 is 25. So log, because like there's log 2 and log 10 and stuff like that. So log 2 25 should result in 5 or log. No, hold on. What's the, let me look at the log functions that they have. Um, so they have log where you can specify the base, I think. The natural logarithm is the inverse of so. Okay. They have log 2, they have log 10. Return the base 10 logarithm of the input so and so. What does this take in? Okay, dude, I just realized I'm getting sleepy, so it's kind of getting hard for me to, that's why it's getting hard for me to think about this. I'm gonna think about this more. I know the answer. I'm just not able to remember the thing. There was a thing that I'm just not remembering. I've done this before. It's just escaping me right now. Which it's fine. It's no big deal. Um, give me a second. Um, right. So I have been. I think I've been to this person's streams before. This is a person named Salad Forest. I think I've been to their stream before. They're cool. They're chill. I, I, I think I remember being to their streams before. So I'm gonna rate this person. That's gonna be it for today. I'm gonna carry on doing some of my. I'm gonna carry on with this research. Hopefully, I might do my sculpting practice today. I don't know if I'm gonna get to it or not. Q10, thanks for hanging out. Thanks for stopping by. Jack, thanks for stopping by and hanging out. I appreciate it. Anyone else who might have been lurking in the chat, thanks for hanging out. Um, I will try and stream again tomorrow. I'm going to carry on with this research. For now, I need to eat something and then relax. So I hope you guys have a nice day, and I will see you all next time. Peace.